This is going to be my breakdown of Chemistry Higher Paper 2 combined. I've already done Paper 1, so it's going to be pretty much the same structure as that one, talking through my thought process behind each of the questions, breaking it down. So if you've not seen the first video, I recommend you go and do that one first, but this one is going to be structured pretty much the same. First question. A student investigated the colours of brown ink using chromatography. As soon as I see that word, I'm thinking separating techniques. So like your filtration and all that stuff. Chromatography is the one where we use a solvent to separate a mixture based on the solubilities, depending on how soluble they are. Okay, so figure 1 shows the apparatus used. Now if you remember, just to remind you, chromatography you should know is the one where you have a beaker, you have a piece of paper, you draw your start line in pencil, you've got water just below the start line but not above it, and then you have the dots of the compounds dotted on the line, and then the solvent, the water, will move up the paper and separate the ink into its components. So let's have a look at this. So there's the apparatus they've used. This picture shows you a bunch of different colours, and then it's asking us to give 2 errors that are made by the student. So 2 things wrong with this. Now we should hopefully know how the proper way to set this up. Now if we have a look at this, we need to spot what's wrong with it. So the first thing we can spot is the start line is drawn in ink when it should be in pencil, right? So that's the first thing we can write down, is we can literally just write start line drawn in ink. Okay, because it should be in pencil. And so that's the error, that's the mistake. What problem does that cause? What would happen if they do that? It would dissolve, because if you remember, the substances we put on the line are also usually inks, so they dissolve. If the line's in ink, it dissolves as well, and it would mix with the solvent, right? Kind of got to be clear about that one. It's dissolved. Where does it go? It spreads into the solvent. This is kind of important. It would mix with the solvent. Error 2, if you remember from the one I showed you the correct way of doing it at the start, the solvent goes above the start line. Very important that that does not happen. So solvent is above the start line. Why is that a problem? Well, if that happens, then same again, the colours are going to mix with the water, they're going to spread and they're going to dissolve into the solution rather than climbing up the page. So colours would dissolve and also spread into solvent. Okay, or the opposite. So because they've spread and it's all over the place, it's not going to climb up. There you go. Next question. A different student set up the apparatus correctly, so they've done it correctly this time. Figure 2 shows the results. We've got a bunch of colours, a bunch of dots, depending on how far. So obviously we know straight off, as soon as I see that, it tells you that, well, these ones are most soluble and then these ones are the least, right? Because depending on how high they climb up, depends on how soluble they are. Give 2 conclusions that the student can make from figure 2 from the 4 colours in the brown ink. So we've got the brown ink, these are the ones where we've got unknown colours, and we need to conclude what can we decipher from this. So the first thing we can decide is the colours that match it. I would do so. That one is matched, that one is matched, that one is matched. So first one is, it contains, so we've got yellow, blue and red, right? Contains yellow, blue and red ink. Okay, one of them is this one here, right? That doesn't match up with anything, so we can also conclude it contains an unknown colour. We could also say So that's 2 marks done already, but you could also say a bit extra. So which we could talk about which ones are most soluble. So blue is most soluble colour. And which one is the least soluble? Well, got to be careful with this one because this one didn't even move. So can you even say it's soluble? So for this one, the least soluble one is actually red. Is least soluble. Green didn't move, so that means it's not soluble. Does not dissolve, right? Won't dissolve in that solvent, whatever they've used. Next question. So why was the green colour still on the start line at the end of the experiment? Well, if you remember, the green was on the start line, didn't move, and we already said if it doesn't move, that means it's not going to dissolve, so it means the green colour was insoluble in the solvent. We already talked about this. A student calculated the RF value of the colour to be 0.24. So the RF value, if you remember, is retention factor. Just means how soluble is it. So it goes from a range of nothing, not soluble at all the way up to a maximum of 1. It's basically a percentage, right? You're always working out, the way I think of it, a percentage of how far the solvent travelled. What percentage did the solute travel, the thing that was dissolving? Because obviously if it went the same distance as the solvent, that would be 100% travelled all the way. That would be a retention factor of 1. So the RF value of this colour was 0.24, travelled 24% of the way up the solvent line, and the colour moved 1.8 centimetres from the start line. So talking about the colour, which is the solute, and we'd be given the RF value. Calculate the distance of the solvent, right? So we're given this and we're given this and we're trying to work out this. So the first thing I would do, if you're good at algebra, you can just rearrange it and then chuck in the numbers, but I would put the numbers in first and then rearrange it. Makes it a bit easier. So I'm going to rewrite this exactly in that order, but I'm just going to put the numbers in. So RF value was, I'm going to replace that with 0.24 because I had a number, equals, I had a number for my colour, was 1.8, so 1.8 over, and then the distance moved by the solvent. I'll just write solvent. Okay, and we're trying to work out this. You could do this in you could do this in one step. If you're good at algebra, I will do it in 2. So first off, I'm going to move that solvent over to the other side from underneath. What's the opposite of divided by the solvent? It's going to be times. So that means the solvent times 0.24 equals 1.8, right? Distance travelled by the solvent. Then we rearrange. So what's the opposite of this? It's divide. So then I'll write it under here. The distance travelled by the solvent is 1.8 divided by 0.24, and you should have got 7.5, I believe. 7.5. Just checking. Yeah. Question 2. Water that is safe to drink is called potable water. Compare how easy potable water can be obtained from wastewater or groundwater. First word I spotted in that, very important, compare. Whenever you see compare questions, especially in science, we don't want a life story on it. We don't want a big long paragraph. The examiner is looking for you to make it as easy as possible for them to give you the marks. So you split it straight down the middle with a straight line like that. And you do one side, so whichever side you want to choose. I'm going to do groundwater on this side. And then you do wastewater on the other side. Okay, so we just do a T-table like that. The other thing that's very important, it's on about comparing. So you need comparative words, right? So you don't want things like easy, hard. You want things like easier / harder, more of this, less of that. Okay, comparative words, make sure you're using those. And the other important thing before I go through this as well is if you talk about, for example, you know, how easy it is, or if you've got expensive or whatever that is, you know, always talk about the same thing on the same line. So you talk about it's easier for this, so therefore it must be harder on the other side. Do it on the same row to make it obvious. So for this one, to start off with, you're going to need to know your processes behind. You should know the process behind getting drinkable water from groundwater and drinkable water from wastewater. You should know the sequence. So for this one, the first thing is groundwater is actually easier to obtain because there's not as much involved, it's everywhere, right? So wastewater, therefore you do the opposite because we're doing a comparison, is harder to obtain, right? Whatever you say for one, you can say the opposite for the other most of the time. Which one involves more processes to get it to the point where you can drink it? Well, wastewater's come from you know what, so it's going to take more processes to get it to the point where you can drink it. So this one has fewer processes, so this one has more processes. Okay, next step I would talk about is how are these two kind of filtered to get rid of the stuff, because think about it in terms of the sequence of what you do to get the drinkable water from it. So the first thing for groundwater is we filter it, filtered through a filter bed. To remove solids. Okay, what do we do in wastewater? It's the step in that one. The very first one is just, remember, if you remember, called screening and grit removal. Okay. Now, there's actually a bunch of extra steps involved in wastewater that we don't need for groundwater, so we can add in underneath that. So in wastewater we use sedimentation to produce sewage, sludge and effluent. Okay, what comes next on that one? We're still not quite there yet. So we've got aerobic biological treatment. Okay, and that is to remove the solid waste from the effluent. I'll just put remove solid waste for that. Okay, now we're getting closer to the point where they're actually at a similar point, because the steps with removing the solids from it are a bit different. So let's go to this. I'll change colour to make it a bit clearer. So then for this one, once you've filtered it and got rid of all the solids, now we need to get rid of the bacteria and stuff like that. So for this one, sterilised with either UV light, you could use ozone or chlorine. Okay, and then for this one you do the same, right? You can just write it again. I would just write it again if I were you. Okay, and then the final bit for this one, extra step, so I'll put it on the bottom if I had. So at that point the sludge needs to be anaerobically treated and digested by a specific kind of bacteria, because at that point you've got rid of all the bad stuff, most of the bad stuff, but you've got to get rid of anything that may still be organic in there to remove, hold on, organic matter. Okay, so it's a bit of a long-winded explanation for that, but whenever you've got comparisons, always put it in a table, make it super easy for them to read the comparison between the two rather than writing a big long paragraph where they've got to try and decipher what you're actually talking about. This avoids you being in the scenario where you're using communication and you might miscommunicate which one you're talking about. You just put it in a table like that, and then it's almost impossible to lose silly marks. A scientist produced potable water from 150 centimeters cubed of salty water. Which process can be used to produce potable water from salty water? We should know this. I mean, it's not going to be electrolysis because that's not talking about drinking stuff. It's not going to be filtration because the salt's dissolved, it's going to get straight through. And it's not going to be sterilization because we're not talking about removing bacteria. It must be distillation. And then the next one. The salty water contains sodium chloride, which is just typical salt. The scientists collected 2.4 grams of sodium chloride from 150 centimeters cubed of salty water. So this is a, what's that? If it's a centimeters cubed, it's a volume, and then this is a mass. Okay. Calculate the concentration of sodium chloride in grams per decimeter cubed. First thing, it says calculate the concentration, so you should hopefully know. This is what I'm thinking. Concentration is mass divided by volume because it's the mass of something per unit of volume. And it also says grams per decimeter cubed, so we have to be careful with that because we can potentially lose marks if we don't convert to that. So I would do that first. So we've got 150 centimeters cubed of the substance. Now, if you remember, a decimeter is 10 centimeters, right? 1 decimeter is 10 centimeters. But when we're converting between volumes, it's a little bit different because we've got cubed involved. So rather than it being obviously to go from, if we wanted to go from decimeter to centimeters, we would times by 10. If we want to go the other, we would divide by 10. But for this one, we're going to divide by 10 because it's a volume. It's 10 cubed, which is actually the same as divide by 1,000. So you convert it first. So 150 divided by 1,000 gives us 0.15 decimeters cubed, which is our volume. That's the hardest bit in this question, and then you just chuck it into the equation. So mass divided by volume, 2.4 divided by 0.15 gives us, answer is 16. This question is about the reaction between sodium thiosulfate solution and hydrochloric acid. As soon as I see that with acid, I'm immediately thinking the whole rates of reaction topic. Probably end up talking about collision theory and all that stuff later on before I even get to it. That's the topic I'm thinking of. So the equation for the reaction is as follows. Sodium thiosulfate plus hydrochloric acid makes sodium chloride, water, sulfur dioxide and sulfur. Okay, the mass of the conical flask and contents was greater at the start of the reaction than at the end. So what's that saying? That is actually saying that we have lost mass at the end. Explain why. So for this, the clue to that would be start looking at the state symbols of the substances that we are using or making. So if we have a look at this, obviously reactants doesn't really matter for this. Why is the mass less at the end than it was at the start? So if we have a look, I mean, that's aqueous, that's going to be in the solution. That's a liquid, it's in the solution. That's a solid, it's in the solution. That's actually what makes it go the cloudy colour. What's not on any of those? It's that one. This is a gas, right? So what does a gas do? A gas just moves, spreads into its surroundings. If there's no bung on the thing, no lid, it's going to be lost. So we can say sulfur dioxide gas is produced. Okay, so therefore what would it do? It would escape the conical flask and is lost to the surroundings. Easy enough. A teacher demonstrated the reaction between sodium thiosulfate solution and hydrochloric acid. So you should hopefully be familiar with this practical setup. Shows the experiment was done in a fume cupboard. Sodium thiosulfate and hydrochloric acid. It's the one where you look at the cross, you wait for the cross to disappear, you time it, see how long it takes. This is the method used. Pour 50 centimeters cubed of sodium thiosulfate solution into the conical flask. Put the conical flask on the black cross on a piece of paper. Pour 10 centimeters of the acid in and start a timer. Stop the timer when the cross can no longer be seen. Repeat the experiment at different temperatures, right? So the question is, what type of variable is time in this reaction? You should hopefully remember your phrase, don't mess in class, right? So remember, don't mess. Dependent is the thing you measure. Independent is the thing you change. And then obviously control is the one you keep the same. So we know for a fact, you don't really have to even think about this one, because what I would do is I would look at this. Right, the first thing it says is we're doing it, the end, it says repeat it with different temperatures. If it's different each time, that must be the independent variable. So it's not going to be that one, right? I mean, if we look at the control, is it the same every time? Is the time that it takes for the cross to disappear the same every time? No, it's not. And that is also what we are trying to figure out, because we are doing rates, trying to figure out how fast the reaction happens, how long it takes. So the answer is dependent. Complete figure 4 graph. Plot the data from table 1 on figure 4. Here's your table. Temperature in degrees Celsius, time in seconds. So then it says you should plot the data from table 1 and you should draw a line of best fit. When you see this, this is telling you where the marks are going to come from. If it's out of 3 marks, chances are you'll only ever get 1 mark from line of best fit. So that means the plotting the data is potentially worth 2. So let's have a look at the scales on the axes first. So the first thing we need to figure out is what are the little jumps worth, the little squares. So if we look at 0 to 10, there are 5 little jumps from 0 to 10. That means each little jump is going to be increasing in 2s. And it's the same for the y-axis, because that's going up in 10s as well. So let's plot this graph. Anytime it's an odd number, think about it's going to be halfway between the little jumps. So 19, temperature 19 is going to be half a little square underneath 20 on the x-axis, and then 82 is easy enough. 82 is going to be 1 little square above 80. You've got to be precise with this, because the examiner can only give you plus or minus half a small square. If you're any more than that off, you don't get the mark and you're losing easy marks. If you're precise with this, it's just easy marks, don't lose them. So temperature 32, so that's going to be 1 square above 30 on the x-axis, and then the time is 48, so that is 1 little square under 50 on the y-axis. Next one, temperature 45, it's going to be smack bang between 40 and 50 on the x-axis, and it's going to be 1.5 squares above 40 on the y-axis, like that. Temperature 52, time 15, so 52 temperature is going to be 1 square above 50, and then the 15 is going to be smack bang between 10 and 20. So that's there. This is why we do this in pencil, because then if we mess it up, we can just rub it out as many times as we need to do it to get it right. 63, temperature is 1.5 squares above 60, and then 7 is going to be 1.5 squares under 10 on the y-axis. So that's there. And then the last one, 73, is 1.5 squares above 70 on the x-axis, and then 3 is 1.5 squares above 0. So there's your plots, done. Next thing we need to do is draw a line of best fit. Now the first thing is, we're in science, we're not in maths, so you can do curved lines, they don't all have to be straight. Another clue as to the fact that it's going to be curved as well is we are talking about rates of reaction, right? And the rate of a reaction is never the same all the way through, okay? So usually a hint that it's rates, sometimes it can be curved, and it's science. And if we look at them plots, they do kind of look like they're making a curve, apart from this one here, which doesn't really make sense to the rest, because I mean, if you look, we've increased the temperature by quite a bit, and then the time has not really gone down. So I'm going to ignore that one on my line of best fit. Now I'm going to do my best because I'm currently on a tablet, but you're on a piece of paper, so this should be pretty easy for you. You do it in pencil, you do it light, and you just kind of have a couple of goes going through it, and then you have a go, right? So you do a curve, go through the plots like that. Okay, carry on. So you want to try and do it in one swift line. I can't really do it on this tablet, but you just get like a, you might have done art before, you get like a curve motion, practice it a couple of times, dead light, and then go. And if you do it wrong, just rub it out. That's the beauty of you doing it in pencil, isn't it? Easy enough. A student investigated the effect of concentration of sodium thiosulfate on the time taken for the reaction at room temperature. Figure 5 shows the results with a tangent drawn at 0.4 moles per decimeter. That's our concentration at that point. So what we need to do is, we've already got the tangent drawn for us. Sometimes you're expected to do that yourself, so that's kind of them. X-axis is the concentration, time is seconds. Calculate the gradient of the slope of the tangent at 0.4 moles per decimeter. First thing I'm thinking when it says gradient, okay, you need to remember is the change in y divided by the change in the x-axis, right? So then what I would do is I would kind of turn this tangent into a little triangle. It's up to you where you want to use it. You can make a small triangle between 0.3 and 0.5. I would just use the full thing. So for that one, that is at 5 for the y-axis, and then if we draw along, let me just rub that out, draw it along, complete the triangle like that, right? So we work out the changes in the y-axis and the change in the x. So change in y is, it's gone from 5 up to 15, so the change is 10 seconds. The change in x, it's gone from 0.1 up to 0.6, so the change in x is 0.5 moles per decimeter. Okay, then we just calculate, chuck them into the equation. So the change in y was 10 divided by the change in x was 0.5, and the answer is 20. So that's your number, right? Now this bit's a little bit trickier because it's asking us to work out the units. So if we just put in the units first, so we have 10 seconds divided by 0.5 moles per decimeter cubed, right? What I would then do is get rid of the numbers. So seconds divided by moles per decimeter cubed. Yeah. You could also rewrite that as, because that line, when you, for example, when you've got meters per second, you did distance divided by time. It's a divide, isn't it? So we could also write it as seconds is divided by moles divided by decimeter cubed. Okay. What happens when you divide a divide? You end up with the opposite, so that would actually move up to the top. So then we would end up with second decimeters over moles. So then that's given your unit. You just kind of move that dash. So your unit would be second decimeter cubed per mole is your unit. 3.5. Student determined the rate of the reaction at regular time intervals during an experiment. Explain why the rate decreased during the reaction. Give your answer in terms of particles. Whenever you see the word particles and rate, the phrase that I'm thinking immediately is frequency of successful collisions, right? What is the frequency of successful collisions and why, if it's changing? So that phrase you need to use probably in your answer anytime this happens. So why does it decrease during the reaction? Well, if we think as the reaction progresses, okay, the reactants are being used up and being turned into products, so the amount of particles that we have as reactants is going to be less and less and less as time goes on. So that's the first thing we can put. Number of particles of reactants per unit volume decreases. Yeah, that's your first mark. Therefore, what was the phrase that we need that we always use to get the second or third mark if it's the third 3-mark question? So therefore, less frequent successful collisions, or the frequency of successful collisions decreases is one way you could put for that. This question is about hydrocarbons and the uses of hydrocarbons. Figure 6 shows a model of an alkane. So that's the one that's single bonds only. So it's not an alkene. And then it says, what is the name of alkane in figure 6? For this one, you only need to remember the first 4 because the rest are easy, aren't they? So the first 4 you need to remember the one with 1 carbon, 2 carbons, 3 carbons, 4 carbons. So first one was methane, second one was ethane, third one was propane, and the last one, the fourth one, was butane. And then after that, 5 pentane, 6 hexane, as in like hexagon, 7 heptagon, hexane. The rest are easy, you just need to remember these 4. How many carbons has it got? 1, 2, 3, 4, so it is butane. Then what is a hydrocarbon? I mean, don't really need to explain that one. The clue is in the name, made out of hydrogen and carbon. Sometimes you get an extra mark for saying only. So it's only made out of hydrogen and carbon. So just keep an eye out for that. I would just put only anyway and get into the habit of saying it, because if it's 1 mark, it's not including that, but if it's 2, you can get an extra mark for saying that. Large hydrocarbon molecules are cracked. As soon as I see that word, I'm thinking cracked means when we're talking about we have a large chained alkane, so the large ones that are not so useful, and then we crack it into a smaller chained alkane, and usually we'll get alkenes. Okay, so we've got when C11H24 is cracked, 3 products are formed. Complete the equation for the reaction. So it's a bit trickier this one because there are 3 products, so that means we're going to end up with a number of possible answers that we could put for this. So the first thing we've got this alkane, and we know that we're going to make this alkene, and then we're going to make 2 of something and 1 of something else. First thing I would do is figure out how many carbons and hydrogens have I got left to play with to see what the products might be. So I would subtract this C5H10 from that starting reactant to figure out how many have I got. So 11 take 5 is 6, so 6 carbons, and 24 take 10 is 14. So we've got this many carbons and this many hydrogens to play with. Then it's a case of you've got to do trial and error to try and figure out a combination that would add up to 6 carbons and 14 hydrogens. So the first thing is, we know because we've got 2 of this reactant coming out, there are certain numbers that we definitely can't use, right? We can't use C4H something because that's too many carbons, because you're going to end up with 8. You don't have that many. You can't use C3H something. I mean, you might be able to, but if we're thinking it in context of focusing on an alkane being produced, that kind of narrows it down for us, because the whole reason we do this process is to get an alkane, because alkanes are more useful. So, well, more useful as fuels anyway. So what we can do is we'll try different numbers. So let's try C2, right? So let's try, for this one, you just trial and error it 2 times, which you could do an alkene. So C2H4, so that's ethene. If we've got 2 of those, right, if we put that there, C2H4, how many carbons would that total? That would be a total of 4 carbons and 8 hydrogens, right? What does that leave us with from this that we started with? That means we've got 2 carbons and we've got 6 hydrogens left. Is this a possible molecule that can work? Yeah, that's ethane, so we can do That one works. You could also try it, what if it had 2 times this? So what if we had 2 C2H6, so 2 times ethane? Okay, does it work? What have we got left? 4 carbons and 12 hydrogens. That would leave us 4 behind and 2 carbons. Sorry, H4. Okay, is that a molecule that exists? Yep, that's ethene. So you could actually do it the other way round, like that. It's just a case of trial and error. Just know that it's got to add up to whatever's left over, which was this, and then see what combinations of alkenes and alkanes you can use to get to that point. Next one, explain why one of the products of cracking is in high demand. So when we're talking about that, it's asking you to specify one of the products that you've mentioned is in high demand, right? Which usually, if it's in high demand, means it's more useful. So you pick one. So if we talked about this one is an alkane, short chain alkane. So short chain alkanes are very useful for fuels, so we can focus on that one. So shorter chained alkanes, and we got to specify. So that's C2H6 is, why is it more useful as a fuel? It is because it's more flammable, so more useful as a fuel. We could also look at this one, ethene. If you remember, you can actually take alkenes and you can make them into polymers, so we could end up with polyethene. So C2H4 can be used as a polymer. Well, we'll clarify, to make a polymer. Okay, why? Because, so this is where your second mark comes in, because they're more reactive than alkanes. There you go. So window frames can be manufactured from wood or from plastic. And then table 2 shows data for a life cycle assessment, for a wooden window frame in comparison to a plastic. So life cycle assessment is all of the resources and energy and effort that goes into making it, maintaining it, and disposing of the waste that it causes. So there's a comparison between the two in the table. Both window frames are the same size. So we've got it talking about these things. Evaluate the sustainability of wooden and plastic window frames. Keyword here is evaluate, so that's talking about what are the pros, what are the cons, and you should include environmental and economic factors in your answer. So that's telling us that to get the full answer, we need to link that, what we are saying in our comparison, to our scientific knowledge, linking it to the environment, linking it to the economy. So we compare the two. So let's start off. We'll focus on plastic for the majority of this, but it doesn't matter which way around. If you do the converse, it's the same thing. So the first thing we can say, let's look at the first one. So we can say plastic. So if we look, wood uses 5.37 kilograms of hydrocarbons for the production, and plastic uses 8.23. So we can first off say plastic uses more hydrocarbons in production. So that's our random blanket statement, and then link it to what you've been learning about in science. What is a hydrocarbon? Hydrocarbon is a non-renewable, it's from non-renewable crude oil, isn't it? So that's going to factor into our evaluation. Okay, so we've done the first one. Let's look at the next one. Greenhouse gases released during production, use and disposal in kilograms equivalent of CO2. Which one releases more greenhouse gases? It's plastic, so that's our next one. So plastic releases more greenhouse gases. During production, use and disposal, we can just say greenhouse gases, link it to our general knowledge in science, which contributes to global warming. So you see the pattern. I'm just saying a lot from the table, dead simple, and then just linking it to what you've been learning about in science. Next one, oxides of nitrogen and sulfur dioxide are produced in arbitrary units. Which one produces more? So we can say plastic produces more nitrogen oxides and sulfur dioxide. Plastic produces more oxides of nitrogen and sulfur dioxide. Okay, linking to that, we can say link it to something to do with science. So sulfur dioxide causes acid rain, and then we've got oxides of nitrogen give you respiratory problems, and they will also contribute to acid rain. Next, so we've done that one, done those first three. Waste materials. So next we've got plastic. Plastic leaves behind more waste. Where does that link to when we're talking about waste? Where does it get stored? All of the waste gets stored in landfills. Okay. Next. Then we've got, so we've done that one. Total energy consumption in production, use and disposal in millijoules. So plastic consumes more energy. Energy for production, use and disposal. Don't really need to say anything to link to that one. Done. And then the last one, lifetime cost to the customer to buy and maintain. So the wood will stay on the focus of plastic. So plastic is cheaper to maintain and for customers to buy. And then finally, because we are doing an evaluation, we need to make a final judgment on it. So what we need to do for this is you look at the pros and the cons. All of the cons are towards plastic for every single one except the cost. So we can say overall wooden window frames are better. Okay. You can even mention that the wooden window frames are not that much more expensive than the plastic window frames, and if we're thinking about in the long run all of the different environmental effects that are negative in use of plastics, the only thing that's actually putting it in the favour of plastics is the cost being cheaper, but everything else points towards wood. So you have to give a valid judgment at the end, is how you get your 6th mark based on what you've said. This question is about Earth's atmosphere and the Earth's resources. Talking about the Earth's atmosphere, there's already a hint as to what's going to happen and what we're going to be talking about. After the formation of the Earth's early atmosphere, the amounts of nitrogen and oxygen changed. Right, before I even read any further, the first thing I am going to be thinking about is the comparison of Earth's early atmosphere and now. So early, it was mostly CO2, some water, about 4% water, and then other gases like traces. Whereas now it's mostly nitrogen, it's about 21% oxygen, and then trace gases. Okay, so the first thing I think, as soon as I see that, what's the difference between it then and now, because it's changed. Explain the main changes in the amounts of nitrogen and oxygen in the Earth's atmosphere. So the first thing we can do, one of them is a lot easier than the other one, and that one is oxygen, because it's pretty much obvious. What has happened to the oxygen between then and now? Then it was almost non-existent because most of it was CO2, and then now there's a lot more oxygen. What process can you think of that takes CO2 and turns it into oxygen and makes the oxygen increase? So the first thing we can say is oxygen has increased. What's the process? You should know. It's called photosynthesis by plants. And then the other one, so we've got nitrogen. What has happened to the nitrogen? If it was a trace gas back then, because most of it was CO2 and a bit of water. So the first thing we can say is nitrogen increased. Why is that? Where did the nitrogen come from? If you remember, we had volcanoes spewing out loads of gases, you know, a bit of water, a little bit of it was nitrogen gas, some methane in there. But because nitrogen gas, what's a bit unique about it, it's unreactive. So that means it spurted out into the atmosphere and then it doesn't do anything and it doesn't change. So the volcanoes is what caused the nitrogen to increase. So volcanoes emit nitrogen gas. You don't really need to explain any further because it's state what changed, explain it a bit, state what changed, explain it. You don't need to go any further than that. You could go into the nitrogen's unreactive, etc., but you're not needed to do that for this question. Describe how coal was formed from the carbon dioxide present in the Earth's early atmosphere. So there's two common things that we can spot here. Carbon dioxide and coal, what do they both have in common? They both have carbon in them. And then there's a hint. What I'm thinking now is you start talking about potentially the carbon cycle, how carbon is constantly recycled by different things, changing into different molecules throughout plants, animals, etc. So how coal is formed from the carbon dioxide. So first thing we need to think about is, where does the carbon dioxide go? The most obvious one, where is it used? It's used by things like plants. Okay, here's a tree, a lovely tree. Carbon dioxide goes in, comes out as oxygen, so therefore the carbon is trapped in the tree somewhere. Okay, the tree dies and then it gets trapped underground, and then pressure, lots of pressure, and that's how it ends up compressed as coal. Okay, so that's kind of where the coal ends up going. So all we need to say is, first one would be carbon dioxide is used in photosynthesis. And then what ends up happening, where does it get used? In plants or trees. Okay, they end up dying, so they die and compressed underground. And then how long does that take to happen? This happens over millions of years. That's 4 marks. Next one, the combustion of 1 kilogram of coal produces more carbon dioxide than the combustion of 1 kilogram of natural gas. So the first thing to think about for that one is, what is coal? Coal is just pure carbon, isn't it? It's just carbon compressed together. What is natural gas? Natural gas is a mixture of alkanes. what's an alkane as an example? An alkane will be C4H10, right? Carbons and hydrogens. Which one has got more carbon in it? This one, coal. So the reason why it ends up producing more carbon dioxide is coal has a higher proportion of carbon. There's more carbon in coal than there is in natural gases. There you go. Metals are extracted from metal ores found in the earth. So things about extract. As soon as you see the word extraction methods, you're thinking things like displacement. Okay, you're thinking things like electrolysis might be relevant in this question. Describe how bioleaching is used to extract copper from low-grade ores. As soon as you see the word bioleaching, immediately I'm thinking there are two methods that kind of link together talking about low-grade ores, and that is bioleaching and phyto mining. They kind of go hand in hand, especially when you're doing this topic. The easy way to remember which one's which: bioleaching begins with a B, that's the one that's using bacteria, then the other one must be, and then the other one, phytomining, begins with a P, that's the one that uses plants. Easy way to remember it. So then we have a look answering this question. I mean, we get the first mark for literally saying it uses bacteria. Now you put the bacteria in the substance, and the bacteria, you don't really need to go into massive detail on exactly what's happening, but what the bacteria does is it makes a solution with what we call the leachate, because it's got oxygen in it. You will end up with copper sulfate. So the bacteria causes a solution that's got copper compounds in it that we can then extract the copper from. So the bacteria produces copper compounds in solution. Okay, and then we need to extract it. How are we going to extract the copper compounds? What are the two methods that you could use to extract? You could use displacement to extract the copper with displacement reactions, or electrolysis. Phytomining uses plants to extract nickel from low-grade ores. So that's one of the methods. You've got phytomining and bioleaching. One little tip for exams is, like we said before, we do B for bioleaching, P for phytomining. Sometimes they will actually unknowingly reveal information to previous questions with a following question. So sometimes if you're not sure of something, it's always good to read in the following questions, especially if it's question 5 point whatever. They might reveal information that reminds you of whatever the thing is that you forgot for a previous question. So just a little tip. The plants contain 0.792% nickel by mass. So whatever mass of plants we've got, 0.792% of that is going to be nickel. The plants are burned to produce ash, and then the ash from these plants contains 4.8% nickel by mass. So calculate the mass of the ash produced from burning 1,000 kilograms of plants, and then give your answer in grams in standard form. Very important for this, because we could lose potentially 1 or 2 marks if we don't do this at the end. Just like you get those significant figure questions or decimal places, be very careful, read the question carefully. So the first thing we need to figure out for this is how much nickel is in this, right? In 1,000 grams of plants. So the first thing we need to figure out is what is 0.792% of 1,000 kilograms. The way I would do that, there's a number of ways to do this. You can do the whole divide by the number and then times by 100. You can do, what I always do is I will always turn it into a decimal place and then times it by that, because it makes it a lot easier. So first thing is, if we remember, 0.01 is the same as 1%. right? If we times it by 0.01, that would give us 1% of whatever it is. So 0.792 would be 0.00792. That is 0.792%. So if we times it by that number, it would give us 0.792%. So the first thing I'm going to do is do 1,000 times 0.00792. It's going to give me 7.92 kilograms. That tells us that in 1,000 kilograms of plant, there is 7.92 kilograms of nickel in 1,000 kilograms of plants. Then we need to figure out how much ash we've actually got. So we know that there's this much nickel in the ash, and we know that 4.8% of the mass of whatever the ash takes up is going to be this number. So that basically means 4.8% of something is going to give us 7.92. So we need to figure out the unknown value. So the way I would do that is same again, turn 4.8 into a percentage, which is 0.048 is the same as 4.8%. So that means if we times something by that number, we're going to get 7.92. So I would actually write that out. So question mark, something that we're trying to work out, the mass of the ash times 0.048 gives us 7.92 kilograms. Then we just rearrange it. So the question mark is going to be 7.92 divided by 0.048 gives us 165 kilograms of ash. Okay, we're not quite done there because we need to times it by 1,000 to get it into grams. So that's going to be 165,000 grams of ash, and then we need to turn it into standard form. The way I would do that is imagine very end of the number, the decimal point will be there. I'll do it in a different colour, so it'll be there. And then we just count how many places we need to move it. So 1, 2, 3, 4, 5. So the answer would be 1.65 times 10 to the power of 5 is your answer. This question is about catalysts and equilibrium. So as soon as I see those words, equilibrium, I'm thinking first thing that pops into my head is the reversible reaction symbol. Catalysts, what do catalysts do? We're talking about rates, we're talking about speeding up reactions. What type of substance is a catalyst in biological systems? I mean, if you can remember the phrase biological catalyst, and we can break it apart. I mean, hopefully you can just know this one off the top of your head, but is it algae? I mean, there's nothing to do with catalysts on that one. Alkene is not biological because that's just a chemical. Formulation is when we've got a specific recipe of something, so it's got to be enzyme, which if you remember this phrase, biological catalyst is what we call an enzyme. So a catalyst in living things. Explain how a catalyst increases the rate of a reaction. So when I see that, I'm thinking this diagram. So energy profile, you've got progress of the reaction and energy. And then you have, let's say it was an exothermic, right? Reactants, products, and then you have your activation energy. And if you had a catalyst, so this is our activation energy. If we had a catalyst, it lowers that activation energy. So less energy needed to get the reaction to start. So that's the first thing we can say is it lowers the activation energy. And your second mark, because you need two things, if you remember, is by providing an alternative pathway. There you go. Reversible reaction for production of ammonia is as follows. That's your symbol for reversible reaction. What can scientists predict using Le Chatelier's principle? So we're talking about this one, we're talking about equilibrium first and foremost. Okay, so the first thing that pops into my head is same rate forwards and backwards, right? Same rate of reaction. So the products are being made at the same rate that the reactants are being made. What can scientists predict? So they can predict the position of the equilibrium. So depending on the amount of products or the amount of reactants that there will be in the equilibrium, depending on if they change different conditions. So we can put position of the equilibrium when changing conditions. Okay. Describe how a reversible chemical reaction is able to reach equilibrium. Well, if you remember, the first thing we know is when we see the word equilibrium, that means that the forward rate of reaction and the reverse rate of the reaction is exactly the same. So rate of reaction is the same forwards and backwards. You could say that the reactants are being used up at the same rate as that they're being made, so the forward reaction and the reverse reaction is the same. And then the reason we can do that is this will only work if we have a closed system, won't it? So if we had a conical flask and we didn't have a bung at the top holding everything in, then you would lose gas, and then eventually you would get to a point where, I mean, that looks a bit like a volcano, but you get the idea. You would end up losing gas and losing reactants or products to the point where you would lose the equilibrium. So you've got to say in a closed system, which just means you could have also put when apparatus or equipment prevents the loss of products or reactants. Explain the effect of increasing the pressure on the yield of ammonia. So we're still talking about equilibrium, so I'm just going to write the symbol equation at the top. So 1 mole of nitrogen and 3 moles of hydrogen, reversible reaction, gives us 2 moles of ammonia, and they're all gas. So for this one, first thing is we're increasing the pressure. Very important keyword for that is pressure. We are talking about moles, so the number of molecules of each of the thing. That's what we're affecting that's what we're focusing on, deciding on where the equilibrium position is if it says pressure. Now, if you remember when we were talking about equilibrium reaction, so as a reminder, the kind of reaction that has the forward reaction happening at the same time and at the same rate. And if you remember, it's like an angry teenager, so whatever you do to it, it will always do the opposite of what you are doing. So you look at when a change is happening in conditions, which direction of the reaction does that favor, then the equilibrium will make it do the exact opposite. So if we increase the pressure, for that one we need to look at which side of this equation has more moles on it, and it is this side, the left side. So we can say what's going to happen is it favors the reverse reaction, so the equilibrium is going to do the exact opposite. So the first thing we can say is there are more moles of reactants. Okay. I would always get into the habit of saying where the equilibrium position is. Unfortunately for this question, you don't actually get a mark for saying that, but sometimes you do. So I would say where the equilibrium position is going to move to. If it is favoring the reverse reaction, then the equilibrium is going to do the exact opposite. So the equilibrium position will move to the right. Okay. I'll put that in a coloured bracket because this one, for this question, you don't actually get a mark for that, but sometimes you do. So always get into the habit of doing that because it'll also help you decide what's going to happen. And then we need to decide explain how that's going to affect the yield of ammonia. Well, if the reaction is moving to the right to favour the other side, that means we're going to get more ammonia coming out the other end. So the yield of ammonia increases. Next one, the forward reaction to produce ammonia is exothermic. So the first thing I'm going to do, as soon as it says that, the forward reaction, so you would have this on your sheet, I've written it at the top. So the forward reaction is exothermic, so therefore the reverse reaction must be endothermic. Explain the effect of increasing the temperature on the yield of ammonia. Now, if you think about exothermic is the one that gives out energy to the surroundings, so you feel it as hot, and then endothermic is the one that takes in energy from the surroundings and you feel it as cold. So if we're increasing the temperature, that is favouring the forward reaction because that's the one that's hot, that gives out the energy. And like we said before, what is equilibrium going to do? It's going to do exactly the opposite. It's going to move the position in the opposing direction to what you are doing to it. So the first thing we can say is equilibrium will move in the endothermic direction, or to the left. Okay, or we can just say to the left. And then that's our first mark. Then we need to decide what's that going to do to our yield of ammonia. If it's moving away, so it's moving to the opposite side of ammonia, it's going away from the ammonia, so you think of it as the yield is going to decrease.